Well, a wave.
Hmm.
Imagine if the very building blocks of the universe weren't just like distinct particles, but shimmering, rippling energy.
Right. Sounds like science fiction, doesn't it?
It really does. But this is actual fundamental physics, and it shapes our whole understanding of reality. How did we even get there, this idea of matter being wavy?
Yeah, it's a fascinating story. It really starts with light and then takes this amazing turn when scientists started thinking, well, maybe those same quantum ideas apply to everything else too.
Okay.
So today, our deep dive is all about that mind-bending reality of wave-particle duality. We're really zeroing in on matter waves, the de Broglie hypothesis, and the huge implications of the Heisenberg uncertainty principle.
And our mission for you listening.
Our mission is to unpack how seemingly solid stuff can also act like waves, how scientists actually proved it, which is a great story in itself, and what that really means for, our grasp of the universe.
And we're using some solid sources today.
We are. We've got excerpts from chemistry and physics LibreTexts, a Wikipedia deep dive on matter waves, even some practice notes on the de Broglie equation, and a lecture from Bihar University. So a good mix.
Okay, great. So we've touched on this before, how light has this dual character. It acts like a wave, think electromagnetic waves, interference, but also like particles, photons getting absorbed at specific points. That was already a big deal.
Absolutely foundational. Planck and Einstein. Yeah.
But what was so radical about taking that idea, which was already kind of weird for light, and saying it applies to matter, was it just a guess, or did de Broglie have some sort of insight back in 1924?
That's a really good question, because it was radical. I mean, de Broglie, in his PhD thesis, basically said, look, if light can do this, why not matter?
Just like that.
Well, maybe not just like that, but he had the audacity to hypothesize that all forms of matter, electrons, protons, neutrons, even whole atoms and molecules should have this wave-particle nature too, this bold idea about symmetry in physics. And he didn't just stop there. He came up with an equation for it, the de Broglie wavelength. Lambda equals Planck's constant h divided by momentum.
Momentum being mass times velocity, right? So lambda equals h over mv.
Exactly. H over mv. Or just h, where the p is momentum.
Okay. So here's the bit that always gets me. If I throw a baseball, it has mass, it has velocity. Does it have a de Broglie wavelength? I mean, really?
You've hit on the key point. Yeah, technically, yes.
Yeah.
Every moving object has a de Broglie wavelength.
But
For something like a baseball, let's say you throw it at, 40 meters per second, the wavelength you calculate is, well, it's incredibly tiny, like 10 to the minus 34 meters.
Which means
it's utterly impossible to detect. It's just astronomically smaller than anything we could ever measure. That's why, you don't see wave effects with everyday objects. The wavelengths are just too small.
Right, you don't see your car diffracting around a lamppost.
Exactly. It's only when you get down to things with really, really tiny masses, like electrons, that the wavelength becomes large enough, relatively speaking, to be measurable and have noticeable effects.
And that's why proving it for electrons was such a big deal.
Precisely. That was the game changer.
So how did they prove it? You can't just, look at an electron and see ripples, right? What kind of experiment shows this invisible property?
No, you definitely can't just look. They proved it using diffraction. It's quite clever, actually.
Diffraction, like with light going through a slit.
Sort of, yeah. So classical physics would say, okay, if electrons are just tiny particles like little bullets, and you fire them through, say, two narrow slits.
You'd expect two distinct bands on the screen behind them where they hit,
Got it.
like paintballs through two windows.
Exactly, two clumps. But that is not what happened. The surprising reality, first shown by G.P. Thompson in 26, and then Davison and Jummer in 27, was different.
What did they see?
When they scattered electrons off atoms in a crystal nickel, in Davison and Jummer's case, or passed them through very small, close slits, they got an interference pattern.
Whoa, interference. Like waves overlapping. You mean alternating bright and dark bands?
That's exactly it. The classic signature of wave behavior, just like water waves passing through two openings, or light in Young's famous double-slit experiment from way back.
But electrons are particles. How does that work?
That's the paradox. Each electron, when it hits the detector screen, makes a single dot. It arises as a particle.
Okay.
But over time, as more and more electrons arrive, the pattern formed by all those dots is an interference pattern. It emerges from the varying density of where the particles land.
So individually, they're particle-like hits, but the overall distribution looks like a wave.
You got it. And it gets even stranger. They did versions with detectors at the slits to see which slit each electron went through. And they found each electron went through only one slit, not both.
You need something going through both slits to get interference, right?
Classically, yes. But somehow, even going through one slit, the electrons collectively knew about the other slit to create the interference pattern statistically.
Yeah.
It's one of the deep mysteries.
That is truly wild. So individual electrons hit like particles, but the collective paints this wave picture. How did scientists start using this then? What did it allow?
Well, first, it basically cemented the whole idea of wave-particle-duality. We already knew light could act like particles, sometimes the photoelectric effect.
Right.
These experiments showed matter could act like waves. Duality wasn't just a weird thing about light, it was fundamental. It meant we could actually use wave equations, using that de Broglie wavelength, to describe how matter behaves.
And the practical applications.
The most obvious and visually striking one is the electron microscope.
Ah, yes. You see amazing pictures from those.
Exactly, because electrons can have wavelengths much, much shorter than visible light, up to 100,000 times shorter.
Which means you can see much smaller things.
Way smaller. Electron microscopes blow light microscopes out of the water in terms of resolution. We're talking resolving things smaller than 50 picometers versus maybe 200 nanometers for light. Magnifications up to 10 million times.
Wow, so it literally let us see a whole new world.
It revolutionized fields. Biology, materials science, designing new medicines, new materials, understanding viruses. It all hinges on being able to see at that tiny scale which electron waves allow. It turned this weird quantum idea into an incredibly powerful tool.
And you mentioned it wasn't just electrons. This wave thing applies more broadly.
Oh, absolutely. It's a universal property of matter, just harder to see with bigger things. Neutron diffraction came along soon after, proposed in 34, seen in 36.
Neutrons, too.
Yeah. They also exhibit wave phenomena. Their wavelengths are often around the same size as the spacing between atoms in solids, maybe 0.1 nanometers, especially if you slow them down or moderate them.
What are they good for?
Great for crystallography, figuring out structures. They interact differently with atoms than X-rays or electrons, especially with lighter elements like hydrogen, which is crucial for biological molecules.
Interesting. And beyond fundamental particles.
Yep. They've shown interference with whole atoms, sodium atoms, back in 1930. And even much bigger things like buckyballs, those C60 carbon molecules,
Yeah.
showed wave interference in 1999. Their wavelength was tiny, 2.5 picometers, but measurable. And they keep pushing it. As of a few years ago, they'd shown wave behavior in polypeptide molecules up to 25,000 atomic mass units.
25,000? That's huge for a quantum object.
It is. It really blurs the line, doesn't it? Where does quantum stop and classical begin?
It really does.
Yeah.
Okay, so if an electron or even a molecule is a wave, what kind of wave are we talking about? It's not water waving, it's not light waving. What is waving? Because when we measure it, we find a particle at a spot.
That is the absolute crux of it conceptually. It's not a physical wave in the way we usually think about it. It's best understood as a probability wave.
A probability wave.
Yes. The wave function, the mathematical description, doesn't tell you where the particle is. It tells you the probability of finding the particle at a particular place, if you were to look.
So the peaks of the wave are where you're most likely to find it.
Exactly. And the troughs are where you're least likely. The wave nature only really shows up experimentally in that statistical sense. You run the experiment many times.
And the particle hits build up that wave pattern.
Precisely. Even if you set up the exact same experiment each time, individual electrons will hit different spots. But over many runs, you get that predictable probability distribution.
That does sound probabilistic, not deterministic.
And that's what bothered Einstein so much. He famously said, God does not play dice. He felt quantum mechanics was incomplete because it could only give probabilities. But, well, so far it seems like nature does operate on probabilities at this fundamental level.
Which leads us directly to Heisenberg, doesn't it? The uncertainty principle. This idea that probability isn't just because we don't know enough. It's fundamental. We can't know everything precisely.
It's exactly right. Heisenberg's uncertainty principle is a direct consequence of this wave-particle duality. The core idea is simple but profound. You cannot simultaneously know both the exact position and the exact momentum or velocity of a particle like an electron.
Why not? Is it just that our measurement tools aren't good enough?
It's deeper than that. The very act of measuring affects the system. To find out where an electron is, you have to interact with it. Maybe bounce a photon off it.
Okay, like shining a light on it.
Sort of. But that interaction, that bounce, inevitably kicks the electron. It changes its momentum in an unpredictable way. So the more precisely you measure its position, using, say, a high-energy photon with a short wavelength.
The bigger the kick and the more uncertain its momentum becomes afterwards.
Exactly, and vice versa. If you try to measure momentum very precisely, using a low-energy photon perhaps, you disturb its position less, but the longer wavelength means you have less precision about where it actually was.
There's a trade-off.
A fundamental trade-off, mathematically expressed as x times ep, is greater than or equal to h divided by 4.
Delta x is uncertainty in position, delta p is uncertainty in momentum, and h is Planck's constant.
Right. The product of the uncertainties has a minimum limit set by Planck's constant. It can't be 0. You can squeeze one uncertainty down, but the other must pop up.
So why don't we notice this in everyday life? When I drive my car, I feel like I know both its position and speed pretty well.
Well, that's because Planck's constant h is just incredibly, incredibly small. About 6.63 times 10 to the minus 34 joule seconds.
Tiny.
For macroscopic things like cars or baseballs, the mass is so large that the inherent quantum uncertainty in position and momentum is laughably smaller than any practical measurement uncertainty we have from, potholes or reading the speedometer. It just gets completely washed out. Classical physics works perfectly fine.
It's the correspondence principle, right? Quantum rules match classical rules for large objects.
Exactly. But for an electron in an atom, it's a different story. If you try to pin down its position to within, say, 0.01 nanometers, which is still bigger than an atom,
Yeah.
the uncertainty in its velocity becomes enormous, something like 5.8 million meters per second. It makes the idea of a neat little orbit completely meaningless.
Yeah.
You just can't track it like that.
So Feynman's quote makes sense. What there are particles.
Right. You detect particles.
But when you look at enough of them,
they arrange themselves in space according to those wave-like probability rules. You can't really say what they are while they're traveling, only what probability you have of finding them somewhere if you measure. The measurement itself is key.
okay, that's a lot to digest about the small scale. But you mentioned this connects to astrophysics, too. How does matter acting like waves affect something as huge as a star?
Yeah, zooming way out, it becomes crucial in very extreme environments.
Right.
Think about the cores of white dwarfs or neutron stars.
Super dense.
Incredibly dense. Matter is squeezed so tightly that the particles are very close together and quantum effects take over.
How so?
Well, particles confined in a small space act like standing waves, like a guitar string vibrating. It can only vibrate at specific frequencies or harmonics.
Right, specific notes, quantized modes.
Exactly. So particles confined in the star's core can only have specific, quantized wavelengths, energies, and momenta. There's only a finite number of available slots or quantum states at each energy level.
Okay.
Now imagine you keep packing more and more particles in. They fill up the lowest energy states first, but eventually all the low energy states get filled. This is the Pauli exclusion principle for particles like electrons.
So where do the extra particles go?
They're forced into much higher energy states, even if the temperature isn't necessarily that high. This creates an enormous pressure called degeneracy pressure, which has nothing to do with temperature. It's purely a quantum mechanical effect.
And this happens when?
The critical point is when the average separation between particles becomes smaller than their de Broglie wavelength. That's when they start significantly overlapping and acting like waves in a box.
And you said electrons are key here.
Yes. In these stellar cores, electrons reach this quantum limit, this degeneracy, much sooner than the protons or neutrons.
Why?
Because electrons are so much lighter. Remember, HMV, lower mass, means a longer de Broglie wavelength for the same velocity or temperature.
I see.
An electron's wavelength is about 40 times longer than a proton's or neutron's in a star. So the electrons start feeling crowded, quantum mechanically speaking, much earlier. Their wave functions overlap first.
And that electron degeneracy pressure is what holds up a white dwarf star against gravity.
That's exactly right. It's a direct, large-scale consequence of the wave nature of matter. Same idea, but with neutrons for neutron stars.
Wow. From electrons in a lab experiment to holding up dead stars. That's quite a range.
It really shows how fundamental these quantum principles are.
So let's recap. We've gone from de Broglie's pretty bold idea, this hypothesis about matter waves, through the experiments with electrons, neutrons, even big molecules that proved him right, showing this inherent wave-like nature everywhere.
Right. Diffraction and interference patterns being the key evidence.
And we saw how this leads inevitably to the probabilistic view of quantum mechanics. These aren't physical waves, but probability waves.
Yeah, telling you where you're likely to find the particle.
And that connects directly to the Heisenberg uncertainty principle, the fundamental limit on knowing both position and momentum precisely, because measurement affects reality at that scale.
A limit set by Planck's constant, negligible for us, but dominant for atoms and electrons.
It's a truly remarkable journey, and it completely overturns our sort of everyday classical intuition about how the world
It
works.
really does. And as we saw, they're pushing the boundaries, seeing these quantum wave effects in larger and larger molecules.
Which brings up a really interesting final thought. If individual particles aren't really waves or particles in our normal sense, but we just use those models depending on how we measure,
Yeah, the mathematical description is the reality, in a way.
then what does that actually imply for the boundary? Is there a sharp line between the quantum world and our everyday classical world?
That's the million-dollar question, isn't it? The measurement problem, decoherence, it's still debated.
And as we get better at seeing these quantum effects in bigger systems, how might that keep changing our basic understanding of what reality even is?
A profound question to leave you with. Where does quantum weirdness end? And does it truly end at all?